So it's my turn. I would like to thank you for organizing this event and for having me here. So my name is Spyridon. Most of you know me probably. I'm currently working at SINTEF Energy Research, but I've been doing my PhD here for the last 3 years at NTNU. So today I'm going to present part of my PhD work entitled this data-informed energy storage sizing and control for wind-powered offshore oil and gas platforms. As we said, we will be mostly focusing on the sizing part. And this is basically based on some relevant publications and other stuff, the links for which you can find at the end of this presentation. So basically for the content, we will first start with a small project description about my PhD project, then what motivates our research and the research questions. Then I will speak about the problem formulation, and I will focus to this core with the scenario generation methodology that is proposed. Then we will have a short overview of some results, and then I will briefly speak, given the time, for irregular events and energy management and multipurpose control of energy storage systems. So basically, my project comes from a collaboration from the Norwegian Academy of Science and Letters and Equinor. The goal is to enable a higher dependency of isolated power systems to renewable energy. And the target application is the wind power offshore oil and gas platforms. Of course, why such application? It combines both being isolated system and has the renewable part. And when speaking about oil and gas industry in general, it makes sense to speak about, to consider the Norwegian case being one of the largest exporters, oil and gas exporters in the world. But where comes the renewable part from? It comes from recent trends of industrial trends to build the wind farms close to the offshore locations of the oil and gas platforms. And from another perspective, maybe you can tell more about it. It's agreed that the battery prices and storage prices are constantly falling, and this is a trend that we see going forward. So what is explored through this PhD project is the proposal to integrate energy storage into such isolated systems and see what are the benefits and what can we extra get from those systems. Okay, but before going into the details, let's get a better visual understanding of what it makes this case very interesting and very complex. Here we can see basically the load for two different platforms and the wind speed for the same offshore location. And from just observing, it's clear that there are no seasonalities. It's very there is high variability and there are no specific cyclic behaviors. Let's say, what goes if we further zoom into one particular part? We see that this pattern of irregularities and the constantly varying load, it's repeated even in a smaller time scale. And even if we further zoom, basically we can notice that there are situations that there are very sudden and abrupt changes, step-like variations that can trouble any kind of prediction for the future operation of the system if we're trying to optimize the future operation short term. So basically, if we are trying to group this data that we saw earlier into daily occurrences, this is the time in hours here, we can clearly see the variability and the complexity that is associated with such systems. For example, here we see the load in a day ahead, let's say, and here we see wind power, which of course has a lot of variability, it's intermittent, and this complicates the situation a lot in every isolated system. So when it comes to the natural question, what is a representative operational situation for a wind-powered oil and gas platform? Because being representative helps us to take decisions when it comes to the sizing and to the design, and also to the control. But yeah. Going back to the energy storage integration, which we said is basically what we are interested. Okay, it has a lot of benefits, and those benefits can span many different timescales. Depending on our perspective and our point of view, we have either the sizing problem, if we are going for the cost-benefit point of view, and if we are going from the operational point of view, we have the energy management problem and the control of the energy storage. What is common to both of these problems is basically that there are common sources of uncertainty, and we don't have perfect information. That's very true in everything, basically. So what kind of sources of uncertainty we have? We have the disturbances, like we said earlier, load variations and renewable injections, power injections. And then from the model, we can have unknown dynamics, we can have uncertainty in the parameters. So both share common sources of uncertainty. However, decisions that are affecting the future must be made here and now, as we say. Those decisions can be either the design of the system or the control commands we are giving for a specific goal. Many alternatives have been proposed. Just to mention some basic, two basic alternatives is if we consider a reference period. So if we take a snapshot of past realizations and we based on our decision based on this past realization. This, of course, has a generalization issue. We are relying very much into what has happened before. Other cases to take the worst case, like from extreme. Yeah.
Can we ask a question?
Yeah, of course. Feel free.
Can you explain about this sizing problem? I didn't get exactly what are the...
Yeah, I will go into that further into the presentation. This will be the focus. But basically what we are trying to do is we are trying to find how big should be the energy storage in order to have like some benefits into the operational stage. So it's an investment. We are going to pay for that and we are going to gain some benefits in the operation. How we decide the power basically and the energy, but this will come into the details later. So yeah, perfect question. And basically, what we are trying to do through this project is to make use of some available data in order to leverage how we model uncertainty and basically how conservative we are. So that's the proposed idea. And now we are going further into the details of this sizing problem. Basically, this is the system. So the system is like a power node. It's the oil and gas consider it as an aggregated load. So we have the aggregated load here, and there's also this damping load. It's for energy stability, for power balance, basically. The power generator is on site, and we have gas turbines that are providing the required energy, and those can be switched off and on. So there are some binaries here. And as we said, in the offshore, in the similar offshore nearby, in this offshore location, there is this wind farm that is providing power to the system. And we are considering the daily operation. So we are trying to say how big should be the energy storage if we are considering the day-ahead operation of such a system. And as it's commonly formulated, if we are trying to integrate the operational states into an optimization problem, we can end up with a two-states problem. So what's the first stage decision, as we said, is basically the investment that we're trying to do. So how big should be the energy storage system to satisfy our goals? And this has two decision variables, the power and the energy. And then in the second stage, we have the operation, which is in an hourly base for the day ahead. And here, basically, we have two kinds of variables, two types. There are some binary variables that are indicating whether we should have on or off the gas turbines that are the unit commitment problem, basically. And then we have also the dispatch, the power dispatch. How much energy should I drag from any of these gas turbines? There are a lot of them, not just one. This is illustrated. And how the energy, basically the power should be split among the different components. And of course, we have uncertainty. We have an uncertain disturbance that we call Xi. I want you to remember this Xi. And it's natural that we go for a stochastic optimization approach since we are integrating uncertainty. Nothing to very look into details here, but I'm just formulating the objective cost in a very standard format. So it's basically a two-stage stochastic optimization. So we have the first stage decision here, and we have an expectation over the second stage of the uncertainty. And this can be formulated into a standard equivalent, basically, that is resulting into a mixed integer linear program where the recourse includes both integer binary variables and continuous variables, because we are solving simultaneously the unit commitment and the energy dispatch problems. What is important, and that's the focus basically, is that this uncertain realization, this disturbance Xi, is composed of two parts. It's one part the load and one part the wind variation. So the load, what we call here with L, we have the superscript, is the load profiles, and what we have with W is the wind profiles. So the requirements is that we want a system that has a realistic uncertainty representation. The limitation, of course, is how do we discretize this stochastic process? And this is, as you know better than me, is commonly done through scenario generation procedures that we are basically discretizing the true continuous uncertainty. So what we said earlier is that we are trying to generalize and we are trying not to stick what has happened in the past, but we're trying to learn from that, the basic statistics. So basically, we are trying to generalize this XC from past data, and that means that we infer a space omega. And then from this space, we're trying to generate scenarios that we call with hat, XC hat, that will belong in this omega S, which will be a subset of this omega, the big one. Why? Because there's an inherent limitation on the amount of scenarios that we can use. If we are considering no decomposition techniques, and if we are considering just the two-stage stochastic optimization problem. What is important? That the objective function, that value of the optimal objective value, is a function of the model that we are using to solve, but also of the input uncertainty space. So it comes a natural question: how big this uncertainty space, this number of scenarios, let's say, should be? And this can be relied on. This relies on the stability criteria, which basically says that we need to have the objective value not moving too much if we are changing the scenarios that we put into the problem in order to solve it. So remember, a scenario that we see hat here, it's composed of two components: the load profile and the wind profile. For example, here we have with green load profile, red wind profile. Different occurrences induce a different scenario. That's completely normal. But we have not only the individual profiles, but we have the combination of those profiles. What this means is that if we take this profile and we change it to the load and we change it with wind, then we have two more additional scenarios. And this is something that will have a completely different solution, probably. It does not guarantee that this is the same as this, of course. Just as an illustrative example, if we try to compute the number of theoretical permutations in this reduced subset, given a discretization level of this, basically, depending on the number of periods that we are considering in the ahead problem, this 24 hours, we get an extreme amount of possible theoretical permutations. So it's kind of, we need to find a way to confine this, but also to preserve all the information, or as much as information as possible. So our target is to define how big this uncertainty space should be and which one in particular should be in order to respect these properties. Okay, so we said the scenarios are defined by two things. The first is by individual profiles. The other is by the combination of the profiles. Alternative methods to do, it's like scenarios by sampling observed data profiles, taking the represented days that have actually been observed from the data sets that we have. Other is that we have scenario by random profile permutations. We are able to also allow for permutation of profiles. Then we can use, of course, scenario reduction techniques, and we can reduce the initial data sets and then select from these reduced data sets. Then we can also reduce the initial data sets by clustering methods, and we can also try to combine different profiles. And others specify that there should be a specific correlation between load and wind. I'm not very aligned with this, but these methods exist, basically. What we are trying to do in our method is that we need a way to, first of all, calculate those individual profiles, these random profiles, basically, that we have not observed before, and then find a method to combine those. So this is the initial dataset for the load that we said for the platform. From that, basically, we can infer some probability distributions with kernel density estimation, for example. And then we have for each hour, for each time period, we can have a marginal distribution. And then we can also model the correlations between those different time instances. Basically, this will define a multivariate probability, but when we are trying to link it with the correlations, we can use basically this copula trick, and we can actually transfer into a Gaussian copula. And then from that, we can actually use inverse transform sampling in order to generate profiles. And those profiles will basically populate this omega space that we said earlier. So this is just in order to generate profiles. This is a way to generate profiles. And we can see that in the end, we are able to replicate the statistics of this data set. So we can, with blue is the initial data set, and with red is basically the profiles that we generate. So we are able to generate as many of them as we want, preserving some statistical properties from here. And this is a way to generalize basically what we have seen without sticking in particular to what we saw. The same we can do for wind. And this is the way to generate profiles for load, profiles for wind power. I want you to focus now on something specific that we are using in this method. Basically, it's related to the scenario reduction techniques. If we apply a scenario reduction on each individual data set, so the load and the wind power, for example, like with fast forward selection of with any other kind of scenario reduction, these algorithmic procedures tend to take the profiles that are as equidistant as possible to the initial set. But this has an inherent difficulty inside that we are tending to select things that are very similar to each other, and that makes us not consider other situations that can actually happen. We see this is very strong for the load profiles, and similarly, even for the wind, we see that there is a general similarity between the scenarios that have been selected from such procedures. On the other hand, if we see this procedure from the other side, we can identify the profiles that are the most distant from the initial dataset, which basically we can select profiles selected to be as distant or as non-typical of their own datasets. And we can see here the red ones are the ones that are more distant in the metric that we are using. So basically what we are doing is that we are taking this concept of scenario reduction in order to rank those profiles. And we can see that, okay, the ones that are selected first are more representative, and then the second is second representative, third, and it goes like that. So in that sense, we can attribute to each scenario that is composed of one load profile and one wind profile just two numbers. And those numbers are specifying how characteristic each profile is from their own dataset. Yeah, and then we can characterize this Xi by these two numbers. So now we have a way to build this omega. We need a way to build this reduced subset that we said earlier. We start from the initial sampled omega that we know how to generate it. Then we map the scenarios to the two-dimensional space that spans basically all the patterns. How do we do that? Is because we said we are ranking them, so we can include the ones that are most descriptive and the ones that are less descriptive, or most typical and non-typical, to put it in a better way. And then we can plot them in this low-dimensional space, two dimensions basically. And what we can do further is we can perform a clustering on this space, which is easy. And then we can end up with this reduced subspace by taking the ones that are characteristic from this plane here. So how do we decide how big this should be, this reduced subspace should be? For that, we have an iterative procedure, basically, that we are using all the previous components that we said earlier. We sample the initial omega. We perform the mapping, the low-dimensional mapping. Then we perform clustering. So we have a reduced subspace here. Then we are we're solving the problem basically many times, and we're checking for the statistical stability. And then we have many different metrics in order to observe and to validate that until we find the predefined convergence criterion. And basically we are doing this procedure many times by increasing every time the amount, the cardinality of this reduced subset until we find the one that satisfies our predefined preferences. And therefore, we have a way to both decide the number of scenarios that should be and what kind of scenarios should be inside this the input uncertainty model. So just to give an overview of the results, here we have plotted the statistical stability results for the different methods that we mentioned earlier and the one that we are using. It is clear to see that, okay, it's important to mention that all of them are for the same cardinality to be a fair comparison. So how big is this uncertainty space is the same for all the methods. And we can see that we are effectively reducing the variability of the output of the objective function, basically. Also, some other trends indicate that, for example, if we are doing a fast scenario reduction technique, and then we are just combining profiles from load and wind, there's a high bias, because as we said earlier, those tend to select similar profiles. If we are using a clustering method, there is the high variance, because basically, again, all the different combinations can end up to different results. But the way that we are doing it is basically we're trying to consider at every time all possibilities and all possible configurations. Just for the numerics, we can basically end up with a solution like with the size of power and energy. And then we can calculate other metrics like the value of stochastic solution. And that's actually something interesting that in the expected case, no storage is optimal for that. So it would be zero. And we can have benefits if we are considering uncertainty into the problem. And of course, there are some other benefits that can be quantified from the daily cost, emissions, curtailment, and other metrics that are just numerics.
So one question on this.
Yeah,
Is it in-sample stability or out-of-sample stability? In-sample. Did you check it also for out-of-sample stability?
No, I had something to do. So basically what we wanted to check is because this procedure is independent of the objective function, and we said, okay, if we apply also a risk measure to control the risk, is there any capability there? Is there anything that we can get? So basically we applied the conditional value at risk measure, and we performed some simulations. And for the risk neutral case, this is the CDF basically of the cost function. Of the cost value, and this is for the risk averse. And basically what we saw is that trying to reduce the worst case cost basically deteriorates our expected benefits, and that makes sense. But what is important is that we need to remember how this reduced subspace that we're actually using looks like, how this looks like in the problem. And this is how it looks like. Basically, here we have plotted for the day ahead the scenarios that are related to the load, the scenarios that are related to the wind, and this corresponds to one scenario. So it's line here is one scenario. So it's a combination directly. And we have plotted them in terms of increasing the cost. And we can see here, basically that those scenarios that are characterized by high load and low wind that are captured from this methodology, that's the important thing, are mapped here, basically. And what was the result from here is that accounting for the expected worst cases lead to marginally high cost improvement and while sacrificing the expected gains. So all in all, it's not worth to have any risk measure here because from this procedure, such situations will be always captured. And in such situations, basically, you cannot do nothing. Going back to the smaller timescales. Yeah, of course. Yeah. And just to mention some additional things that for the lower timescales is the operational problem, basically, and is the control problem. For that, we consider again the same system, but now in a higher detail. And what we are doing is we are trying to find an optimal energy management system that is basically able to compensate for these irregularities in the load, like the sudden variations that we saw earlier. The way that we are doing that is by using basically quantile random forest. And as we see here, it's basically this allows us to have a method in order to anticipate those sudden variations and generate uncertainty that is depending, actually, it's adaptive. And then we can solve the problem in the loop. So we integrate that into a stochastic model predictive controller, and then we can have some benefits. Whoever is interested can look into the corresponding publications. And then what happens in the even smaller time scale, since we already have the energy storage system there, is it possible to do many things simultaneously? Let's say to provide some ancillary services and at the same time follow the reference state of charge that's being given from the upper scale energy management system. For that, we design again a controller that is basically trying to achieve both of them under the presence of uncertainty again and under some guarantees. I will not give any further information. Whoever is interested, we can have a discussion and we can look at that. So basically, everything is here, all contact information, all references. Yeah, and thank you very much for your attention. I would be very happy to have a discussion. Yeah.